Okay, the last conic section we're going to talk about is hyperbolas, 7-3. So the contrast between ellipses and hyperbolas is the first thing we're going to start with. Ellipses and hyperbolas tend to be very, very similar in some of the algorithms and formulas that we have for them, but there are definite differences that we really have to pay attention to. So first, when we define an ellipse, we talked about earlier the locus or the set of all points such that the sum of the distances from two foci is constant. Well, with a hyperbola, it's a little different, but not much. The locus of all points in a plane such that the absolute value of the difference between two focus points is constant. So the absolute value of the difference between foci is constant. And they say the absolute value because it doesn't matter which way you subtract, it's just really looking at the difference. They want you to look at the positive difference. Okay, both have two axes of symmetry. We know that the major axis in an ellipse has a formula of 2a. Well, with a hyperbola, there's something else that has a formula for 2a, but it's called the transverse axis. Okay, it is not necessarily bigger, and we're going to make a note of that. As in an ellipse, the major axis is definitely bigger, but in a transverse axis and a hyperbola, that's not necessarily the case. The minor axis in an ellipse has an equation or a formula of 2b. In a hyperbola, we call that the conjugate axis. It also has a formula of 2b. Okay, the relationship between A, B, and C, there is also a C value, which has to do with focus points for a hyperbola. And the relationship in an ellipse is a squared minus b squared equals c squared. But in a hyperbola, it is actually the Pythagorean theorem exactly. A squared plus b squared is equal to c squared. Okay, so we're going to take a minute and label all the parts of the following hyperbolas. So as we look at this first one, this hyperbola is horizontal. It goes to the side. And the one on the right is a vertical hyperbola. It goes up and down. So as we look at these two hyperbolas, let's take a look at the first one first. And I'm going to slide this up so we can see some of the differences in their algorithms below. So looking at the one on the left, the horizontal, a hyperbola, just like an ellipse, has focus points, but they're going to be located on the insides of the hyperbola. And the center is right here in the middle, not on the hyperbola, but right in the middle of those two pieces that are facing away from each other, like two parabolas. And that center is referred to as HK. And we can look below and see the center is HK down there in that chart. So the ends of the hyperbola that are closest to each other make up what we call the transverse axis. It is an imaginary line. It is the distance between the two vertices. So this is a vertex, and this point is a vertex. A parabola just has one vertex, but a hyperbola has two of them. And so the two vertices on either ends, they make up what we call the transverse axis, and that's in the third or fourth row down. The length of the transverse axis is 2a. So from the center to each vertex has a length of a. Okay? Then we have what's called the conjugate axis. Now you're going to see this light blue dashed square or rectangle, and the conjugate axis is actually going the other way. It is perpendicular to the transverse axis, and so the conjugate axis would have points here and here, top and bottom of that rectangle, and the distance from those points to the center is b. And those are also considered co-vertices. We don't use that term as much with the conjugate axis or with hyperbolas like we do with ellipses, because literally those endpoints are on the function or on the conic section itself. So the length of the conjugate axis is 2b. Now the length of the distance from the focus point to the center, once again, is c. Okay. Now, the asymptotes, which are here in this pink or red color, they do have slopes. They are lines. And the way that we get these slopes, I'm going to go over with you in just a minute as to why they are a over b or b over a. But the slope is positive or negative b over a. And here, the slope is positive or negative a over b. So if we look at the rise over run, as I go from the center to the corner of that rectangle, I rise b and run a. I rise b and run a. So the slope would be positive and negative b over a because I go in both directions. Okay, and then the relationship between a, b, and c is very different. Well, not really very different at all. Sorry about that. It is actually the Pythagorean theorem. A squared plus b squared equals c squared, just like we said earlier. And so there's that relationship. Okay, now look at the vertical one. We're going to label the same types of things. Again, we have two vertices. So my vertices are going to be here and here. The vertexes or vertices of each part of the hyperbola. So there's a vertex, and there is a vertex. Again, now our transverse axis is horizontal, and the length from the vertex to the center is a in both directions. So that's why we can say the length of the transverse axis down here, fourth row down, the length of the transverse axis is 2a. There are also focus points inside the hyperbola, which would be on the transverse axis if it was extended. And then out to the center is still right there in the middle as HK. And then out on the ends of this box, the other way from side to side, this would be our conjugate axis. These are co-vertices, and the distance from the center to each of those is b. So the conjugate axis has a length of 2b. Then the slope of the asymptotes. If you look from the center to the corner, you rise a and run b. So we can say the slope of those asymptotes would be positive or negative a over b. Okay, now one thing we want to notice, how do you know when it's a horizontal hyperbola and when it's a vertical hyperbola? So we want to look at the equations. Notice, like an ellipse, they're both equal to 1. But now these are both subtraction. With a hyperbola, you have subtraction instead of addition. And then notice that the denominator in both of them is a squared first and then b squared. A squared first and then b squared. And what changes is in the horizontal, you have x minus h all squared first, whereas in the vertical, it comes second. And then in the first one, you have y minus k coming second, but in the vertical, it comes first. So why is that? Let's look at how we can tell what's going on. So in a hyperbola, a squared is always first. Rather than bigger, like it is in an ellipse, a squared is always first. So a squared does not move, and what you want to do is look right above the a squared, and whatever variable is up there, that's the direction of your transverse axis. So when we look for the horizontal transverse axis, you look above a squared, you have an x. So that means your transverse axis is side to side, horizontal, and so that's the direction of my hyperbola. If you look at the vertical, above the a squared is the y, so my transverse axis is vertical, and my hyperbola then is vertical. Okay, so now let's work some examples and graph these. Okay, so graph the hyperbola given by each equation. All right, so we first have y squared over 9 minus x squared over 25 equals 1. So we know that now with a hyperbola, the first denominator is always a squared. So a squared is 9, making a 3. 25 is my b squared, making b 5. Now if I look above a squared, I see a y. So that means this is going to be a vertical hyperbola. The transverse axis will go up and down. When I look for the center, the HK, there isn't one, it's just y squared and x squared. So my center is actually the origin. We're going to plot that right there. The transverse axis, which we know is vertical, is going to be 2a units long, which is 2 times 3, which is 6. So from the center, I'm going to count up 1, 2, 3. There's one vertex, and I'm going to start that hyperbola there. And 1, 2, 3 down, and again, I put some little starters on it so I don't forget. The conjugate axis, which we're going to need to make the box to draw our asymptotes, has a formula of 2b, which is 2 times 5, which is 10. So to the side, I'm going to go 5, and to the other side, I'm going to go 5, and then I'm going to make my box, including those 4 points, top of the box, the side of the box, the bottom, and the right side. So I use the transverse axis and the conjugate axis together to make a rectangle. Sometimes it's a square, not always. Most of the time it actually is a rectangle. So now, to make those asymptotes, you simply go through the diagonal, which goes through the center. There's one asymptote, and the other one is the other diagonal. Now when I know that this hyperbola is vertical, I'm going to go back to the vertices, and I know that asymptotes steer the behavior, so I'm just going to approach those vertices for my graph, and there you have it. Now, if they wanted to know the slope, positive or negative a over b or b over a, well, we're just going to count from the center to the corner of that box. You rise 3 and you run 5, so it would be positive or negative 3/5 would be my slope. And if they wanted focus points, I would take a squared plus b squared equaling c squared. So 9 plus 25 is equal to c squared, which is 34, equaling c squared. So c is the square root of 34. And what you would have to do, you would have to add that to the center. So if the center is 0, 0, I would say that my focus points, or foci, would be 0 and positive and negative root 34. And so that's going to be 5 something. 1, 2, 3, 4, 5. So it would be kind of right in here. You do not need those to construct the graph, so that's just kind of a little bonus there. All right, let's look at B. We're going to graph this one. We have x plus 1 all squared over 9 minus y, this should be a plus 2 all squared over 16 equals 1. So my a squared is 9, always coming first in a hyperbola, and this is b squared. So b is 4, and a is 3. My center is going to be -1, -2, and let's find my transverse axis. So this has a formula 2a, so 2 times 3, which is 6. Now the transverse axis, if I look above a squared, it's an x, so this parabola will be horizontal. Okay, so I'm going to plot my center, -1, -2, and I'm going to go 3 to the right and 3 to the left. And there's going to be the start of my hyperbola. Then I need the conjugate axis to help me finish off that rectangle or box to draw my diagonals. That's 2b, which is 2 times 4, or 8. So I'm going to go up 1, 2, 3, 4, 1, 2, 3, 4 down, and then I'm going to draw this box, this rectangle, so that I can draw the diagonals and have my asymptotes. So right down through the diagonal, and because I know that this goes horizontally, I'm going to make a symmetrical hyperbola side to side. So the slope, if you had to answer the slope, it would be positive or negative. Now go do rise over run. It would be 1, 2, 3, 4 over 3. So positive and negative. 4/3 would be the slope. My foci, or focus points, my center is -1, 2, but my focus points are going to be to the side. So it would be the x value that's changing. So it's going to be something -2. Well, to find that something, remember a squared plus b squared equals c squared. And so I have 9 plus 16 equal to 25. Okay, and since we have a c squared of 25, that means c is going to be 5. So we're going to go from the center, and we're going to count 5 to the right. 1, 2, 3, 4, 5. There's a focus point. And 1, 2, 3, 4, 5 to the left. There's another focus point. So we're counting from -1, so it's -1 plus or minus 5. And because that's an integer, we don't really want to leave it like that. So we do want to list them out in two different ways. So -1 plus 5 would give me 4, -2. And -1 minus 5 would give me -6, -2. And there are two focus points. Okay, let's go to example number 2. So we're going to graph the hyperbola that's given by this equation in standard form, and we're going to write it in our other form where we have x minus h all squared and y minus k all squared. So we're going to get the x's together, and at the same time, I'm going to factor out the 25 and the 16 from my x squared and my y squared. So as I factor out 25, I have x squared. When I factor it out of the 100x, I have plus 4x. I'm going to leave a space, and then I'm going to factor out a -16, and I will have y squared minus 6, and so 6y, sorry. And so then I'm going to leave a space, and that's going to equal 444. So when I take half the b term, half of 4 is 2, and squared is 4, so that's plus 4. But when it's 25 plus or times 4, that's 100. So I'm actually going to come over here and add 100 to the right-hand side as well. When I take half of -6, that's -3, and squared is 9. And then when I do 16 times 9, that's 144. So I'm also going to subtract 144. So now when I simplify the left, I have 25 times x plus 2 all squared minus 16 times y minus 3 all squared. And that is equal to, I'm going to add 444 plus 100, which is 544, and then subtract 144, and that's 400. Since I have to set this equal to 1, I'm going to divide everything by 400. So 25 divided by 400, 25 and 400 reduce to 1 and 16. So now I have x plus 2 all squared over 16 minus 16 and 400 reduced to 1 and 25. So I have y minus 3 all squared over 25 equal to 1. So now that I have this in standard form, when I graph this, my center is going to be at -2, 3. I believe. So let me just make sure that I did this. Yeah, okay. So I have -2, 3. And when I go to look at which way this is going to go, my transverse axis, again, is 2a. Well, my a value is actually a squared is 16, and so a is 4. So 2 times 4 is 8, and when I look above the 16, I have an x. So from the center, I'm going to go side to side. My transverse axis will be horizontal. So my center, -2, 1, 2, 3, there's my center. I'm going to go to the right 4 and to the left 4. So 1, 2, 3, 4, there's one vertex. And 1, 2, 3, 4, there's another vertex. Okay, my conjugate axis is to b. B squared is 25, so b is 5. So 2 times 5 is 10. So I'm going to go up 5 and down 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. So now I'm going to draw my box. And I'm going to draw my asymptotes. So diagonals through the rectangle in the center. Will allow me to graph these hyperbolas. So I'm going to create a symmetric hyperbola on each vertex. And there we go. And again, if they want the slopes, it would be rise over run. So we rose 5 and we ran 4. So the slope of these asymptotes would be positive 5/4. Okay. Let's look at example 3. Now we're given some characteristics and we want to write an equation. So we're going to sketch what we have. The vertices are -3, -6. So 3 to the left and down 6 is a vertice. 3 to the left and up 2 is a vertice. So I know my hyperbola is vertical. If these are my vertices, then I'm going to look at the distance between them. So from a -6 up to a +2 is 8 units. So my transverse axis, which has a length of 2a, that's equal to 8. So my a value is 4, and I know that a squared is then 16. So just getting some of that information. I can also determine the center at this point. So half of 8 is 4. So if I'm at -3 on the x-axis, I'm going to come down 4 from 2 and up 4 from -6, which will put me at -2. So there's my center, -3, -2. So I can start writing this equation. I know that my transverse axis is vertical, so I'm going to fill in this template, y minus k all squared over a squared minus x minus h all squared over b squared equals 1. So I'm going to plug in my center and my a squared right now. So I know that I have y minus a -2 is +2, and let's see, then I have my a squared of 16 minus x minus a -3 is x plus 3 all squared. I don't know b squared yet. So what I do know is some focus points. I haven't had to use those yet, but my focus points are -3, -7, so one more down from the vertex, and -3, +3, so one more up. So my c distance is actually 5. So when I look at a squared plus b squared equaling c squared, I have 16 plus b squared, which I don't know, and c squared is 5 squared, or 25. And I can see that b squared would be 9, and that would be the missing piece for my equation. Okay. Now, if you want, go ahead and pause the video and try b on your own. All right, so what we have in b, we have vertices at 3, 2, and 3, 6 with a conjugate axis length of 10 units. So I know my conjugate axis is 2b, and that's 10. So I already know that b is 5, and I'll probably need b squared to be 25 eventually. So we'll get that out of the way. So my vertices are at 3, 2, and, I should move that down just a little bit. Let's move this down here. 3, 2, and 3, 6. So we're at 3, 2, and 6. So vertices mean that my parabola will be vertical. So I will have y minus k squared coming first. And then I will have my over a squared minus x minus h all squared over b squared equals 1. Okay, so if I have my two vertices, I know that the center is somewhere right in the middle here. So my total distance is 4. So halfway is 2. So if I back down from 6, 2 units, I'm at the center of 3, 4. So it's over 3 and up 4 is my center. My a value is 2, so a squared is then 4. Okay, so now we're going to put this all together in this equation, and we have y minus 4 all squared over 4, which is my a squared, minus x minus 3 all squared over b squared, which is 25, and that equals 1. And there's the equation for a hyperbola with those characteristics. Okay, just like we talked about with ellipses, hyperbolas also have eccentricity. So the formula for eccentricity that we used for ellipses will be the same for all conic sections, and that again is E equals C over A. The difference between elliptical eccentricity and hyperbolic eccentricity is that eccentricity of hyperbolas will always be greater than 1, versus ellipses will always be between 0 and 1. Okay, so example 4, determine the eccentricity of the hyperbola given by y minus 4 all squared over 48 minus x plus 5 all squared over 36 equaling 1. So this is my a squared, this is my b squared, which I'm not going to need for eccentricity, and I do need a c value for eccentricity. So I have a squared plus b squared equals c squared when I'm working with hyperbolas. So 48 plus 36 is equal to c squared. So that's 84 equaling c squared. And so c is the square root of 84. Okay, so I have a then being the square root of 48. So there's a couple of ways to simplify this. Normally with eccentricity, we work it down to a decimal. So c over a, honestly, if you want to do the square root of 84 over the square root of 48, you're going to get approximately 1.32. Not a problem. However, if we want to simplify this just a little more, because normally we do simplify our radicals, 84 is 4 times 21, so we could write that as 2 root 21 over 48 is 2 times 24, or 4 times 12, 16 times 3 is what I'm looking for. So 16 and 3, perfect square is 4, times the square root of 3. So the 2 and the 4 cancel, the 4 becomes a 2, and 21 over 3 divides to be root 7. So for the exact eccentricity answer, it is root 7 over 2. But typically we do these with decimals, so approximately 1.32. Okay, so the last part of the lesson is to identify conic sections. So when you're just simply looking at equations, we want to be able to tell what conic section it would form just from the characteristics. So here is that big long equation that characterizes the general form for any conic section. And we want to give some definitions to what we're looking for the following. If we have a line, which we don't see that very often, but that is no term being squared. If everything is to the first power, you just have a line. If you have a parabola, it is either x squared or y squared, but not both. Okay? For a circle, you're going to have x squared and y squared, for sure. You're going to have the same sign for both of those coefficients. So x squared and y squared will have the same sign, and they will have the same coefficients. For an ellipse, you have an x squared and a y squared again, but they have the same sign, both positive, but they have different coefficients because, again, there's a major axis and a minor axis, so there's not one radius all the way around. Okay. A hyperbola, you do have an x squared and a y squared. You just simply have different signs. One is positive and one is negative, and that's a giveaway for a hyperbola. Now, what I do want to make sure that we point out, because these are easy problems to do, but there is one thing you have to remember. If you are looking at x squared and y squared together in one equation, you want to make sure they are on the same side. How about no E in on? Same side of the equation before looking at their coefficients. That is key. Okay, so let's look at these examples down here. It says to identify the type of conic section from its equation. So I have two squared terms. I have an x squared and a y squared. However, they are different. The coefficients are different, but they do have the same sign. So when you have the same sign but different coefficients, this is an ellipse. In equation number 2, I have 4x squared and 4y squared, so I have an x squared and a y squared. They are the same sign and they are the same coefficients, so this is a circle. In equation number 3, I have 2y squared, so just one squared term, that is a parabola. And in the last one, 3x squared minus 3y squared, so they have different signs. Even though they're both 3's, they are not the same. One is a positive 3, one is a negative 3. And if the bottom line is, if they have different signs, it is a hyperbola. Okay, so this takes us up through the end of chapter 7 and conic sections.